We got FRQ number 2 from the AP Chemistry exam from 2026. Part A here, they want us to take a look at figure 1 here, and then they tell us that this is the Lewis structure of the chromate ion. And then figure 2 is then going to be us drawing the resonance structure for the chromate ion. So for part A here, we have two questions. For the first question, it says, based on the Vesper theory, predict the molecular geometry of the CrO42- ion. We count the domains. We got 1, 2, 3, 4. We know that corresponds to sp3 hybridization. And if we're sp3 hybridized with 0 lone pairs, that is then going to be a tetrahedral molecular geometry. For double I, they want us to draw the complete Lewis diagram for the resonance structure for the chromate ion. And then they tell us specifically that out of the 4 oxygen atoms, 2 of them are going to have a formal charge of 0, and then the other 2 are going to have a formal charge of -1. So based on patterns, any oxygen with 2 bonds and 2 lone pairs has a formal charge of 0. So for those ones, we're going to be able to draw our double bonds with the 2 lone pairs. And then any oxygen atom with a -1 formal charge has a single bond with 3 lone pairs. So the remaining ones are going to look like this. They don't want you to calculate the formal charge, they just want you to complete the diagram. Let's tidy this up a little bit. So then these ones on the top and the bottom are both 0 for their formal charges, and then the ones here on the sides, those are where you actually bear the -1 formal charges. For part B, they say that when the chromate ion is reacted with a strong acid, like HNO3, the CrO42- gets converted into Cr2O7- and H2O in a reversible reaction. They want us to write the balanced net ionic equation for this reaction with a strong acid. So you can use, I guess, any generic strong acid, but they give you one here, the nitric acid. So we're going to go with that one. And this reaction has a lot going on. So in order to start with it, we'll just write our reactants and our products. So we have HNO3 reacting with the CrO4 with the -2 charge. And then they tell us what the products are, where it gets converted into this with the same charge. And then we get water as well. So just by looking at this, we can see, well, where's the nitrate? So the nitrate has to go somewhere. We're going to throw the nitrate ion as a third product from this reaction. Now we have to balance it. So if we take a look, there's only 1 hydrogen on the left, but we have 2 hydrogens in the water. So that means we automatically have to double this. If that doubles, we then have to double the number of nitrates on the right. And then on the right side, we have 2 chromium atoms in our ion, and we only have 1 on the reactant side, so we have to double that as well. So then now, that is our overall reaction. So now we're going to write the complete ionic equation, where we break everything up into their respective ions. So let's include our states of matter here, where this is aqueous, 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 liquid, and aqueous. So because this is a strong acid, we know that it ionizes 100%. So we get 2 moles of H+, and then 2 moles of NO3-. This is just an ion here, so then the ion makes its way down. So then we have 2 moles of the CrO4-, and then we have another ion, so it just gets brought along for the ride. And then water, because this is weak, it is not strong, it will not ionize 100%, so we include it just as its covalent form. And then we have another ion, so then we bring down our 2 moles of the NO3-. Okay, so then now, this is the complete ionic equation, so we need the net ionic equation. So then we cancel out our spectator ions, right? We have the nitrate ions on both sides. That's the only thing that is consistent. So now we go to our net ionic equation, where every 2 moles of H+, that's going to react with 2 moles of the CrO4-. That is then going to yield 1 mole of the Cr2O7-, and then we also get water. So this is our balanced net ionic equation, where you have 2 moles of each reactant, and then you only have 1 mole of each of our products. The second part of part B, double I, is asking, is the reaction a redox reaction? And then justify your answer based on the oxidation number of specifically the chromium atoms. So we can think about the 2 ions that are the source of our chromium on the reactant and the product side. So we know the sum of the oxidation numbers is going to equal the net charge. So for the first ion, it's -2. So chromium is only a single atom, so it's just X. And then we have 4 of the oxygens, and then according to our oxidation rules, each oxygen, when it's bonded to a metal, is going to have a -2 charge. Oxygen is very consistent. The only exception is when it's peroxide. It's not peroxide here, so it's going to be -2. And then so we have a little bit of fun with algebra here. So then this becomes -8. So then that means the the chromium here has to then have a +6 charge in the Cr04 2-. Then we do the same process, but for the other ion. But if you take a look, we know that we have twice as many chromiums here. So the sum of the oxidation numbers is still going to be -2, right? We have 2X now for chromium, and then we add that to the 7 oxygens, all with a -2 charge. So then we get -14. We bring that over, and then we simplify this, divide by 2, and so it is still going to be +6 per chromium atom. So I'm going to go ahead and I'm going to say no, this is not redox, because Cr has an oxidation number of +6 from start to finish, or as a reactant and as a product. So this is our justification according to their prompt here, specifically 1 in chromium as our evidence or as our justification. Part C is then saying, based on all of this information given above, this whole new scenario, is the reaction represented by equation 2 thermodynamically favorable or unfavorable under standard conditions? So they give us the equation, and then they give us the respective cell potential of this reaction. So based on the cell potential, we can see that it's negative, so this is going to be unfavorable. However, they want us to justify our answer with a calculation for delta G. So then we use our handy-dandy equation sheet, and then we know that delta G is equal to N times F times E cell, and then this whole term is going to be negative. And so we plug in our numbers, right? N is the number of moles of electrons, so from the balanced equation, we know that's going to be 6. So for every 6 moles of electrons, we then multiply by Faraday's constant. Faraday's constant is 96,485 coulombs per mole of electron. And then lastly, we have the cell potential, which is given, and then that's going to be -1.32 volts. So this whole term becomes positive because of the 2 negative signs. So then we get positive 764161.2 kilojoules per mole of reaction. And then so that is our evidence here, where now because delta G is greater than 0, it is going to be considered unfavorable. And then we have our calculation to justify our prediction. For part D, they want us to calculate the number of grams of chromium solid that could be plated onto the surface of a steel rod when 15.0 amperes of current is applied for 3,250 seconds, and then show the work that leads to this answer. So we're going to start with seconds, and then we're going to work our way from left to right to cancel out the units, so we finally end up with grams of the chromium solid. So then we have the 3,250 seconds. And amperes can really be broken up into coulombs per second. So then it's 15 coulombs per second. And now we want coulombs to cancel. So when we use Faraday's constant, so then we get 96,485 coulombs per 1 mole of electron. And then we use our balanced equation to say that for every 6 moles of electrons, we'll have 1 mole of the chromium solid. And then our last step is then converting moles of chromium into grams using its respective atomic mass. So then from left to right, we multiply, divide, and multiply again, and then we end up with 4.38 grams of chromium, assuming that we have consistent current for the 3250 seconds. Part E says, in a separate experiment, an iron wire is placed directly in a solution of 0.50 molar of our Cr2O7 minus with a pH of 1.99. The concentration of that ion remaining is recorded over time, and then the results are given to us in the graph below. All right, so then if we take a look at our y-axis, we have our molarity of our ion, and then the x-axis is time in units of minutes. And they want us to explain how the data in this graph supports the conclusion that the reaction is first order with respect to our ion. So there's a couple of data points here that we really want to look at. So we know if it is first order, that is consistent with a half-life decay. So that over a fixed amount of time, 50% of our sample or our amount will decrease. So at time 0, we have 0.50 molar. So then we want to look, okay, well, at what time do we see half of that amount remaining? So then we go down, we see 0.25, and then that corresponds to 20 minutes. Okay, well, that's assuming one half-life took place, so let's see if it's consistent. So we do the same thing, so then half of 0.25 is 0.125, so then we look here. Magically, we have a data point that corresponds to that amount, and then that is at 40 minutes. So it looks like our time interval is consistent, where at every 20-minute interval, 50% of the concentration decreases. So we would use that as our justification, where between these points in time, right, from time 0 to time 20, and from time 20 to time 40, we have a decrease by 50%. And then according to this relationship, this is exponential decay. So we would say that the graph represents an exponential relationship. Which is consistent with a first order reaction. With respect to our Cr2O7 2-. We flip to the next page, and then it gives us a new figure. And then so they tell us that we have the natural log of the molarity over time now. So part F, they say calculate the value of the rate constant, K, for the reaction. Now, they don't tell us that we have to use this graph. On the equation sheet, there is an equation where you can solve for K, assuming you know the half-life duration. But we know that K is also just the slope of the graph. And so if we calculate the slope based on the plotted points, that should be our K value. And then it says report your answer in units of 1/minutes. So then, and then show your work that leads to your answer. So I chose a couple different data points, right? So it's really any two data points that you want to select. I chose the ones that were kind of easy to interpret, right? So at 3 minutes, we had negative 0.80. And then at 15 minutes, we had negative 1.20, right? So slope is rise over run. And so your K will then be equal to the slope, or K is then equal to the negative slope. So then I'm choosing those two data points where K is now equal to our value here, subtracted by our value here, divided by these values here. Right, so then we simplify, and then we get 0.0333 minutes to the negative first power. That is then going to be our answer. You should get this same K value no matter what two data points you pick, right? So like I chose the second and what is that, the fifth one or the sixth one. You could have chose these ones. You could have chose the one in the middle because that one also falls on a really good line. No matter what data points you pick, the 0.0333 is going to be our K value. For part G, the student then runs a second trial of the experiment under identical conditions. However, they use a different initial concentration, which is 0.25 molar. Figure 4, which is the graph we were just looking at, they want us to draw the plotted points of the natural log versus time based on the new initial concentration. So K is constant, assuming we're not changing anything else. So we're then going to be able to have our new initial point, right? And then they already plotted that point for us, right? So it's already there. Now we just have to say, okay, well, how are all of these new points going to compare? So these two lines, these two plotted data points should be parallel to each other. So we know that K is going to be 0.0333. And if we're starting at negative 1.40, we should end the same distance between these two plotted points. So our final data point should then be about here. And then so we draw our data points in between. And I know it's hard, right? They specifically say carefully draw the plotted points, but like I said, like it should be a straight line. It should look like a straight line, and your ending point should be here. Because if we take a look at the difference between these 2 points, right, like this is negative 0.70, and then this is negative 1.30, so we get a difference on the y-axis of about 0.60 for magnitude. And then so if we're starting here, we should end about that same difference, about 0.60, and then so we should end at our negative 2.0 point. My line doesn't look super straight, but I would assume that College Board takes this into account, and they're looking for, I would say, the initial, the final, and then a pretty parallel line with the given slope for the original figure.